Good morning again. My name is Savas Kaya. I am a professor at the Electrical Engineering and Computer Science Department. I have the unenvious job of dragging you a little more detail through the details of the semiconductor chip manufacturing processes, a little more. But I want, before I start doing that, let me just kind of comment and so first of all, remind you of the bigger picture and also comment on a few things also Dr. Rahman mentioned in a slightly different context. One is our overall purpose for this workshop and introducing you through all this detailed steps is to understand these types of skills people will need to work in this industry, okay? Meaning there's quite a wide breadth of depth of skills needed, and hopefully as one learns about this detailed names and practices, you could understand that everybody has different angles and useful options to contribute. The second is, as Dr. Rahman mentioned, this is a complex operation, we admit that, but at the same time, when you build a $10 billion manufacturing plant for chips, you have a lot of multiplicity. Many of these instruments, many of these processes have like not one, but multiple dozens of them working at a given time. So if one fails, you could shift maybe the load to the other working systems, and then you take care of the broken one, for instance. So while it is high pressure job, I accept, at the same time there's multiplicity, much like I think aviation industry works with. Avionics systems in planes are always, critical systems have additional needs. The last thing I wanted to add is also that, for instance, the Intel works actually in teams, so you develop skills in a team, and this was amply emphasized by Intel jobs. You need to work in a team, and communication is important, and a team basically makes sure that everybody knows the required skills and the tools properties. So what essentially is a team can really function around the clock when they are assigned 4 days a week and they are 3 days off. The next day they work 3 days and they are 4 days off. So while it's a high pressure job, they I think manage the complexity and the pressure by a very flexible and reasonable sort of work hours across a week rather than a day. So Dr. Rahman has done really good job introducing and getting you maybe familiar with some of these names. Again, I'm going to repeat them in slightly different context or details, but I want you to be aware of some of the generality here, meaning that while we have multiple processes, while we have many processes, they go around and around repeated. As Dr. Rahman also mentioned, 100 times or more to create essentially a city of extremely large complexity. If you look at the modern chip today, and I will do something maybe unorthodox, go to the very end of my presentation. This is how modern chips look like. And if you look at this, it's just like a modern city plan, except that you have 10, 20 billion residents. They are the transistor logic elements, and they are all connected with extremely high number of highways and streets, and they are working at 25 layers of metallization. So that's the complexity managed with lots of signal traffic at the end of the day. So it's a very large system, and then as you could see also, this is Apple M1. I'm sorry, I think this is new M3, but Apple's latest chips, Apple designs and the TSMC produces it, and as you can see, they are entire system. These chips have not just the computational elements, not just the memory, not just the wireless communication, not the new AI tools, etc. Everything working in one chip. So this is additional, chips are not just only complex, they are also getting bigger to a certain extent. Okay, let's get started in this, some of the names so we will keep hearing. And this is my agenda. I'm going to keep to the red material, and the packaging will be introduced later. Dr. Rahman already mentioned some of the concept that somebody else has to design the masks, prepare the circuits elsewhere, and manufacturer engineers just responsible of building them. And as you saw on the videos, this is a picture. I believe this is the very factory Dr. Rahman actually worked. If I wasn't sure, this is from a Cyprus. But today, as you saw on later videos, this is kind of little older technology. You don't want human beings in the fab if you can avoid them. Just needlessly walking around, because we happen to be the most probably risky elements. Everything is robotics, everything is clean. We can bring dirt, contamination, we can create maybe a confusion in a finely programmed system. And the entire fabrication sequence starts with the wafers being prepared. Again, wafers are prepared elsewhere. They come as slices ready for us to start building. And then we keep going around and around those processes that we talk about. And that includes basically adding layers. And when we add layers, some of those layers could be conductive, some of the layers could be insulating, some of the layers could be semiconducting. And then we have a very intricate number of patterns which represent the circuit complexity. And that patterning is the lithography that you saw the video, and the lithography defines how small you could do things at the early stages of the chip especially, and that determines the name. When you buy a new computer, a new cell phone, they mention, oh, we have 10 nanometer chip, we have 7 nanometer chip. That tells you how small they made the most critical dimensions in the chip, and that shows you how new is the technology. So, let me, let's watch this video that will summarize the whole process again before I can speak to it. Let's see, somehow it didn't get picked up. It was working when I just played it. Let's see. Well, I guess, enable editing. Enable contact, that was it. It was secure. Okay, so you just show a security feature, because when you put active material somebody has placed in it, it can have damaging payload, digital payload that can harm your computer. And this is actually another aspect. Today's modern chips have to have all the security features, because chips themselves are an asset, and they also need to make sure they run safely.
This microchip can take up to 26 weeks to make. In its as many as 100 layers, billions of transistors are packed into an area the size of a fingernail. They're the brains behind almost everything we use in our increasingly electronic world. Here's how these complex, tiny devices are made. The process begins with silicon-rich sand. Why silicon? Silicon is a semiconductor. It's the sweet spot between an insulator and a pure conductor. That means its properties, such as its conductivity, can be altered by adding impurities or doping to meet the needs of different electronic devices. This also allows us to control the electrical signals that pass through. Silicon is also abundant. It's one of the 10 most common elements found on Earth. But much of the silicon found in the wild is chemically bound to oxygen, so the two elements must be separated. The sand is combined with carbon and melted in crucibles to produce carbon monoxide and 99% pure silicon. After further processing, ultra-pure silicon is produced. Next, a seed crystal is placed in contact with molten silicon. As the seed crystal is slowly pulled away, silicon atoms are deposited on the bottom surface. The result is a large cylindrical boule, or a single crystal ingot of pure silicon. The boule is then thinly sliced into wafers. Silicon wafers typically have diameters of 1 to 12 inches, with the most state-of-the-art facilities being able to produce wafers up to 18 inches in diameter. Bigger wafers are, of course, able to yield more microchips. Once the silicon wafers are cut, the production process begins in full. Microchips are made in extremely sterile conditions, free from contaminants such as dust. If even just one particle of dust makes its way onto a silicon wafer, the entire batch is at risk of being ruined. This would derail a process that can take an average of 12 weeks. The first step of the production process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the surface of the wafer. Then the silicon wafer is prepared for lithography by coating it with photosensitive and light-resistant materials. The next step is very critical: exposure. The prepared silicon wafers enter a lithography machine and are exposed to UV light passed through a reticle containing the chip's blueprint. The areas exposed to light are hardened, while unexposed areas are then etched away by hot gases to leave a three-dimensional microchip. The electrical conductivity of different parts of the chip can also be altered by doping them with chemicals under heat and pressure. This process can be repeated hundreds of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each chip on the wafer is then tested for performance before it's separated from other chips on the wafer by a saw. Since microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an electrical charge. Resistors help control the electrical current. Transistors can either amplify or switch the electrical signals passing through. For more advanced chips, like those found on high-end graphics cards, there can be upwards of 28 billion transistors on board. More transistors on microchips allow them to send out more instructions, increasing the computational power. Moore's law predicts that computer chip manufacturing would advance at a steady rate, allowing transistor counts to double every 2 years. Based on the sheer power of the technology we use on a day-to-day basis, this decades-old prediction seems to still be mostly true. Manufacturers have been shrinking down their transistor sizes to fit more onto chips. Each breakthrough in transistor size has allowed the production of more powerful chips for our phones, computers, and gaming consoles. In recent years, they've gotten each transistor down to as small as 8 times 10 to the power of -8 inches in diameter, allowing an amazing 50 billion transistors to be crammed onto a single chip. Manufacturing microchips is truly one of our most complex feats, and yet innovations are happening every day.
Okay, so with that, we can, basically I have included a couple of other videos that may be informative, summary at different levels of complexity. I believe this first one is especially good for high school students, for instance, to watch. But basically, you have already been introduced to this general cycle. Let's go into some of the important processes and look them in a little more detail. Obviously, modern semiconductor fabrication environment, the fab itself, the cleanliness, and then the technicians that are dedicated to these banks of instruments and working in parallel is key. Team management is key, resource management and supply chain management is key. So you don't have to be just technical person to work in semiconductor industry. There's a lot of management, there's a lot of human sort of control aspects as well. But let's look into this complexity in a very simplified fashion. This is basically a straw man drawing of a chip complexity, okay? But if we understand the straw man, I think we can understand more complex drawings. Ultimately, what we want is this yellow material, the wafer, the silicon wafer, to have a number of layers come together to create electrical switches. Because we have wall switches to turn the electricity on off, right? Have the light on off. Just like that, when we work with logic digital systems, as you know, all digital systems are working with binary numbers, zeros and ones. So we only count up to 10 because we have 10 fingers. We have kind of had that as a kind of setup, base 10. We know in math you can count in different number systems, and all digital and electronics is using binary systems, zeros and ones. 0 and 1 is essentially electricity is present or not, current is flowing or not in electrical circuitry, and that we need to manage. And that is managed by this little guy called transistor, which allows electrical current to pass between the two ends as a function of the switch in the red, in the middle. We have resistors. This is cross-section. This is how it will look from the top. All these different colors refer to different processing mask steps. We don't do all this complexity in one layer. Remember, we do by 100 layers of step-by-step progression. At any given layer, we are working with one of these colors of mask. If you overlay them all on top of each other, this is what you see from the top. So our process is very simple here in this kind of 4 layers, basically. But mask is nothing except this XY plane filled with different shapes, polygons typically, but also round shapes in some processes. And the top is, this is top view, this is the cross section. You are seeing a metal line on top of a red material. We'll see is a polysilicon, which is a form of silicon that we can make it very conductive by putting lots of impurities. And the process in reality have no 4 masks like that. As I said, typically modern processes may have upwards of 50 masks used. And these are the 4 layers. So active area means that the oxide is cut out. Oxide is the silicon surface is oxidized and passivated. Where you cut it out with the green boxes, you can now insert additional elements to improve the conductivity of silicon. The red element is the polysilicon, a form of silicon we add, we deposit to make it very conductive and work as an alternative gate. This is all technology. We don't use the polysilicon anymore as much in modern processes, but still use in specific contexts. Then you add metals, the last layer there, okay. That is for conductive highways, and I told you there's 20 layers of this in 2025, because you have imagine a metropole like Los Angeles. We have a lot of traffic problem because we are working on 2-dimensional, 1-layer traffic, right? And in a mega city of a chip, 30 billion residents, you need 10 layers of traffic to 20 layers of traffic for all signals to go every which way. And the black layer, the 3rd layer, is the cuts you create from one metal layer to the next metal layer vertically. So you need to connect the 20 highways to each other vertically with little ascending and descending pathways, vertical, and that's the basically black layer that is creating a cut before you fill it with the metal, for instance, connecting the 2 ways. Ultimately, you create a transistor. Here's the transistor that, and you may have heard a name called CMOS, complementary metal oxide semiconductor. Metal is the gate here, oxide is the insulation layer underneath, semiconductor is silicon. So this device is creating all these 0-1 switches in digital logic. This is the one that is responsible, for instance, even when we have flash memory, we have this nice flash USB memories, right? It can take 32, 64, 128 gigabyte of data. All it does, it has a version of this MOSFET with double DAC gates, just like London buses, and then they basically store charge in one of these gates, and then while the other one is done the reading. So how does this work? Electrical current want to flow from one end to another, but it is only allowed when the middle node, the gate, is the right voltage, 1 or 0, to let it go or not, basically. And we have 2 flavors of this MOSFET. We can make it P-type or N-type. N-type means it's electron rich. What is traveling in this arrow direction is electrons. In the other P-type, it is the lack of electron in the system that travels in the opposite direction, much like an empty seat goes around in a full theater. By others taking the empty seat, leaving behind theirs on their own. So the P-type and N-type is essentially one is have electron in excess in the system, the others have electrons in deficit. If you do all this right, you don't just get MOSFET. You get, actually, for instance, resistors. What is the resistor? Let me go back. Resistors can be of different types. Remember, resistor is a fundamental electrical device. We all may have seen maybe Ohm's law, which is voltage equals current times resistance. So that is the resistance, and it's basically, it tells, it's a linear proportion between the voltage and current in an element that conducts electricity. And we can make resistors in 3 different ways, even in this simple process. How can we do that? For instance, if I go back to this, red material, this green material is silicon contaminated with a precise impurity that has 1 level of resistance. You can use it for high resistances. You have polysilicon, which can run as a resistor, as a medium level of resistance, and you have metal that is running across as a very small value of resistances, for instance. And what else we fabricate in this process? We can have capacitor, a conductor separated with an insulator to another conductor. There's a capacitor here. There's a metal, that metal, and this is semiconductor. There's a capacitor here, and we can also have a capacitor between this conductor and the below. So we have different types of capacitors depending on the value we need, etc. And what else we do? We do other devices like diodes, which are P-type and N-type semiconductor junctions in connection. We'll mention that a little bit. We have always talked about MOSFET, but there's another transistor. When Dr. Rahman showed the 1947 original invention of transistor, that was the bipolar junction transistor. Those transistors were easier to make, but they are not very good for building 20 billion of them in one chip. That's why we switched to MOSFETs. MOSFETs are good in putting down on chip in billions and gradually scaling down, whereas bipolar junction transistor, very good transistors, still used in a lot of functions around the perimeter of the transistor, but they're not really friendly for logic operations because they consume more power. And they don't get small very easily. Okay, one of the most important, that was the broader broader context for chip manufacturing, so we're going to build these devices. Let's look into the process steps. One of the most important steps is cleaning. Because what you don't want is you do these 100 level layers, one operation, one layer, one mask, or another operation, another mask. You don't want to contaminate one process by the previous process. So you need to do copious amount of wafer cleaning, and we have specialized cleaning procedure. There's some pictures here. This is basically largely a chemical bath, very finely basically polishing or very finely removing the top layers, either by submerging a batch of wafers or using a single wafer in a special surface cleaning apparatus, so that you want to get rid of anything that doesn't need to be there, basically. I give you an example. We use in photolithography, we'll mention we use something called photoresist. It's a light-sensitive sticky material. We want to use it when we want to do lithography, but afterwards we want to absolutely get rid of it because it's a sticky resin, basically, that doesn't need to be there. So there's lots of cleaning happening. Now, I don't want to bore you with the chemical details, but there's very precise. One is done for RCA. Is a company which invented, I guess that's why it's still called. This first layer of RCA cleaning is mostly for organic and metal, and the second type of processing where you have this precise ratio of the acid and DI water and hydrogen peroxide to remove metal and metal hydroxide species. So because there's a lot of chemical treatments, there are leftovers of metals, leftover of organic stuff, leftover of other materials that we need to precisely make sure that we get rid of, okay? A copious amount of rinsing, and you always blow dry with nitrogen. You don't want to oxidize unnecessarily. So that's kind of the process. The oxidation is the second process. We start the wafer with bare silicon. We want to passivate where everything else doesn't need to be conducting. And that's done globally, as we mentioned, by heating in high temperature. But you could also pick, either you could do this in oxygen environment, pure oxygen gas, or water vapor. And if you do in water vapor, it turns out to be working faster. Okay, so it is better for building faster oxide, but it turns out that dry oxide, the oxygen-only cooking of the wafers, is higher quality in performance. So you want to really do this only at the very beginning when you need very high quality oxide for gate insulation. This turns out to be an interesting process because what happens is oxygen arrives from the top, meets the silicon, right? And that meeting is early on easy because oxygen is right next to the silicon. But as you grow the silicon dioxide, that's the green layer, it adds up to the surface. It consumes 46% of the silicon, and it grows out 56% of the overall green thickness. So what does it mean is you're consuming silicon, and incoming oxygen or water vapor isn't finding easy to reach to silicon anymore. So it's a self-limiting process. So it gets exceedingly difficult as you go on and on. It gets slower because oxygen have to travel all this distance, and that's why we heat it high because they can get. And these things happen in very precise, clean environments of silica, quartz, basically crucibles, heated with inductive heating of coils, typically, and then the gas is provided in exact measure and then make sure that you get clean oxygen. And the systems look like this. You could see that these ovens are essentially, furnaces are sort of elongated, wafers are loaded, and robotic arms are pushing them about 1 minute. I think about early on especially, they need to go very slowly because you're going from room temperature to 1000 degree, 1100 degrees C. So wafers can crack actually if you just push them suddenly. So it needs to be safely done, so slowly done, at excruciatingly slow speeds as you load it and unload it. Here's some technical detail just in case you're wondering. This is wet oxide. Wet oxide means using the water vapor. This is dry oxygen, basically just oxygen gas. And this is how much oxide you grow on the y-axis. Look, so human hair is about 70, 80 micron on average. 50 to 100 micron your hair will be thickness. So if you split, my hair is thick, if you split it 100 times you get a micron. That micron is here. And if you do this micron growth, look, it will take you about, at 1100 degree, about 1 hour, 2 hours, 3 hours, or 4 hours in dry oxygen. And if you want to do it, in wet oxidation, if you want to do it in dry oxidation, it would have taken 100 hours, impractical. So you do oxide growth, the thermal growth, in thin amounts, typically we work around tens of nanometers or less, okay, typically. So it's a slow process. You do the wet process, the water vapor to accelerate it. Next, lithography. By the way, at any moment, if you think you could, you'd like to ask a question on the technical detail or the meaning of it or the process, please stop me, because I have tended to speak like a bullet train. Okay, so that's oxidation to passivate. But how do you then give shapes, all this intricate city? How do you get the streets and the buildings shapes formed on this using lithography process? As Dr. Rahman aptly introduced us, this is a light printing, using light to print. Essentially, light is what we have been using, but we could generalize this as radiation. A radiation source, beam is sending basically energy downward in waves, and then it's being absorbed by a surface material in a selective manner using masks, basically. Okay, so the mask must be pre-made. Somebody has to make those masks, design them first of all, make them and make sure they are correct. And masks of Intel chips or any big manufacturer are protected in Swiss banks, the original masks, literally, because they are the most valuable thing. And you never use the original mask. You make masters, sub-masters and sub-sub-masters that go around in the fabs to be used and redone as they get consumed, because they are also get old and they get damaged over the use. And then you have this material. Okay, if you look at the top right there, the whole process is maybe explained a little more. You have the blue layer, the photoresist layer. That is the material that senses the light and responds to it, either by becoming more soluble or less soluble. And that is defining whether it is P-type or N-type photoresist, okay? Negative or positive photoresist. Light is introduced over the wafer, which has this oxide layer, as you can see with the yellow. Wafer is shown with the pink, and it comes through a mask. Mask blocks part of the light, and lets go other parts of the light. Where it's exposed, the photoresist will react and give you that opportunity either to wash it away or lock it in, depending on which type of photoresist you use. And the net result will be shapes that you can see on that photoresist layer, which will be essentially the blue layer has been changed to this basically violet color there. And basically that is after being exposed and developed. And then you use that layer to basically etch away what is underneath and get rid of what you don't need after the process is over. These are the pictures of some of the shapes up close. If you look at the microscope, optical microscope, you will only see, of course, large features. Very fine features will need electron microscope. Today we work with less than 10 nanometers, so you couldn't see those 10 nanometers with even with the optical microscope, but they will look like this. Typically, the thickness of the film changes its color. That's why you see also some materials are conductive, some of them are silicon dioxide, polysilicon, etc. They have innate different color contrast between them.
Excuse me.
Yes.
About the thickness of this insulator, how if the thickness be more or less, or we are looking for a special thickness?
Typically, the gate insulator under the gate, which does the 0, 1 or 0 logic, we are looking at typically 2 to 5 nanometer today. 1 nanometer, we used to go down to 1 nanometer. We found that insulators don't work as insulators when they are so thin even.
Oh, okay.
So, but as you go between the devices, if you sandwich one wire from another wire, typically we may be on the range of 10 micron with deposited oxide, because you want them far further apart so they don't couple to each other electrical signals.
So we decide about it based on our design and what we are going to
Absolutely. Which layer you are, whether you are doing the early layers or later layers, yes.
So, I mean that it is a one, we just consider the maximum or the safe thickness, or no, for any client
The
that
safe,
is looking for
minimum
special
safe
design?
thickness.
Okay,
Minimum safe
minimum.
thickness when you're putting many 20, 25 metal layers for interconnectivity. In the early on in the transistor, the gate on 0-1 switch valve, you want extremely thin as you can get away with.
No.
Without, but as you make the insulators very thin, they tend to be leaky. So you want to make it thin, but not so thin that they don't work anymore as insulators.
So then my other question is that before going to lithography, after we have the position, I believe that it shouldn't give us a smooth surface of insulator. Before that, we don't do anything to make sure about
Very
that?
good question. We'll come to that. So early on, it's very smooth because wafer is blank.
Yeah.
But as you keep building things become topography. It's like a city. There are high-rise buildings, low-rise buildings. We need to do something about it. I will mention about that. It's called chemical mechanical polishing. So we do actually a polishing layer to make sure it's flat before we can apply lithography.
So
Because
here they skip that, because before going to this...
yes, before doing the lithography, we need to flatten the surface.
Okay.
Otherwise, because what happens is, as things get so small, remember we are pushing the limits of how light can travel from smallest openings called diffraction. That process is also leaves us vulnerable to where we have the focus. If you focus light here, it is in focus, but if you go only maybe 100 nanometer below, it's not in focus. So you need to planarize the wafer. We call it planarization polishing. Well, that's an important step.
Sorry, my last question. I believe that this semiconductor that has a band gap, it will have the electron that jump between this band gap when it is exposed to wavelength. So this wavelength doesn't any distraction for semiconductor.
So when you're doing lithography, you inject light. Surely semiconductor produce electrons on whole pairs,
So what we do
but
is
then
that-
they dissipate over time a little bit, because they don't have anywhere to go. You don't extract them out of device. They kind of roam around each other. They are positive and negative. They attract and recombine again.
Then coming back to the hole.
Yes, yes. If you're not extracting them, just like the solar cells, we extract them. If you don't extract them, they will meet each other randomly and then go away, dissipate over some couple of seconds probably.
Okay.
Or you know, faster. Some of them will initially you have lots of them will immediately meet and maybe in microseconds, nanosecond, but it may take full couple of seconds for all of them to eventually die out. Okay, so what happens in lithography is you want a mask that permits light or stops light, and you expect everywhere it goes through one effect, where it doesn't go through, no effect. But reality is we get not a square profile, we get this blurred profile. And that's what the diffraction is all about. That's what limiting how small we could do. And all this, extreme UV lithography system, I believe, what is it, $200 million it costs fast somewhere, is to get to such small wavelengths so we can squeeze the light from small features. That's otherwise you get blurred. What happens if two things next to each other like this blur, the shoulders meet and the middle region is also exposed. So you don't distinguish them.
Would it be possible to just put like a cover right in front of because the problem would also be the light going to the other.
So to the side?
Yeah.
Unfortunately, what happens, there's fundamental limits. The diffraction is, you cannot get around the diffraction that way. Diffraction is a fundamental property where light scatters to higher angles by just going through narrow slits. That's a fundamental limit that you cannot get around. And that's where actually wave nature of light also exposes itself. You tend to think the light as a particle, like going down in a straight path, but it is not actually. That's when it becomes obvious. So lithography tools can vary. What you saw and the light exposure we've been talking about is what we generally use, but there are other lithography tools. Photolithography is using of light, and micro contact printing as well. You could basically do a couple of things. You could bring the light and mask and the wafer in contact. That's what the micro contact. You get a little more higher accuracy that way. Or you can project the light, much like that projector, over an image, and that is a little larger. This is dimensions. That's atomic dimension, that's human hair, that's what the minimum feature size today are. We have electron beam lithography, which something is on the right is being shown, where we use not the typical light, we use the electron beams actually go and create shapes. Now, if you accelerate an electron in a vacuum environment, it accelerates so much energy, and from its quantum mechanical property, its wavelength, associated wavelength, is extremely narrow. So it can pass through every narrow slit that we would need in a practical sense. But the problem is this becomes a different engineering, and benefit of the electron beam lithography is you can now steer this electron beam X or Y just by putting a voltage that way or that way, and then you can actually go make shapes precisely using a computer on the XY plane. The problem though, you are only doing one pattern at a time. You're not, so when you have a projector like that, the light comes in all the field, right? Everywhere. In electron beam, you're only making one dot, and the dot is scanning line by line. Lines scan the whole field, so that it's slow. It's very precise, but it's slow. But it's why I mentioned it, because that's how we use what we use to make the masks. How do we make the masks that have those 10 nanometer features? We use the electron beam lithography to make the mask. And masks have to be done this way. Electron beam lithography is also very research-friendly tools. We have one upstairs. We bought an old SCM and converted it, took control of the beam and to make shapes. So you can actually make 30 nanometer features in a university lab. You don't need to pay $200 million, okay? And whether you have the contact, whether you have the light source, the mask, and whether the mask touches, there's a little gap with the projection optics. These are different ways of exposing the wafer. All important. And what happens in manufacturing environment, not in the research, you have typically projection systems. Why? Wafer is wafer is free to move. You move to the wafer to the next location, you project again. Wafer moves to the next location, you project again, so that you can make hundreds of chips in one go. Because we can't project the entire 450 millimeter or 18 inches in one go typically. And this is projection-based systems. We have one system like that, smaller version in our lab. You will see in this afternoon. And these are some of the electron beam type of features that were created using electron beam lithography. These features are 40 nanometer, okay? And over here, there's a gap. I can't quite read it, but that's probably around 30 nanometer gap between two metallic objects. And there are electron beams, they have dual beam. One is a big beam, one is a tiny beam, so they can make the larger structures easier, and tiny things are used for the tiny beam to make more elaborate shapes. So these are different types of lithography systems. Lithography system is the kind of very limiting process, a very limiting or determined process, because it tells you how small you can make things. By the way, this is the source of trade wars that's going on between the West and the China, for instance. We don't, Chinese companies are, for instance, are currently not having access to extreme UV lithography, because that's very strategic, very high capacity electronics can be done with that, and obviously we are worried about its intended use. Doping. Okay, the next thing is, let's say we have shapes we can make, and we selectively etch green layers in my 4-layer map. Green layers are open on the oxide. So we have oxide everywhere was passivated. We open windows, green windows, where we're going to introduce conductivity changes. Those conductivity changes will come from the doping, which is introduction of foreign atoms or impurity atoms into silicon. So you don't just open silicon to invite any atom. We work very hard to keep the silicon clean. We only invite phosphorus or arsenic for N-type, electron-rich environment, or we do boron for P-type, electron-deficit environment creation on silicon. So silicon is opened up in windows and introduced, and if you do this right, basically N-type semiconductors will have an extra electron because their impurity atom has an extra electron handy, whereas the electron-deficit one, hole we call it, electron-deficit is hole. Hole is basically coming from boron. For instance, in this case, boron has just the right energy and amount. Basically, it creates one less electron bond, and therefore there's a bond in the system that is open, and that open bond goes around like the empty seat in a full theater, people taking up to occupy, let go their seats, for instance. If you create these N and P regions in contact with one another, all the sparkling, all the fireworks go in semiconductors. So the most quintessential semiconductor, simplest semiconductor devices is p-n junction. Solar cells, LEDs, okay, or other devices we call diodes, all based on this p-n junction. And all interesting things happen in the middle. You can see why. One side is electron rich, the other side is electron deficit. They want to interact. They want to, excess electrons want to go to the empty seats. But as they do this travel across, they leave behind ions that are, they have originated from some atoms, right? They set up basically an electric field. When they start leaving their location and as basically call them back with an electric field as in the opposite direction. So this process is bound come to a halt. It doesn't proceed endlessly. Electron-rich layer becomes electron-rich, hole-rich region becomes hole-rich still. In between we have depletion where electrons and holes met and recombine and annihilated one another. And in the middle is the depletion region where the space charge, the electrons and holes giving atoms basically create a field opposing this mass migration. If you do this, this is what happens. If you put more and more and more impurities, this is per cubic centimeter. So in a given cubic centimeter of crystal, basically we see that the lowest impurities we can get to with cleanliness limits is about 10 to the 14. With all cleanliness, we find that 10 to the 14 impurity atoms per cubic silica. But remember, This is actually 10 to the 23, 10 to the 24 atoms per cubic centimeter inside the crystal. So that's magnitudes of orders of magnitude lower. But what happens if you increase the impurity concentration, whether N-type or P-type impurities, resistivity comes down. Resistivity comes down. This makes resistance lower, conductivity higher. So semiconductor is becoming more and more like a metal. And that's key for its operation. And you could do this in two ways. You could use the heat to basically introduce dopants into this region that you open in the window, open in silicon dioxide, or you could shoot them, literally shoot them like accelerated ions. We have ion guns, basically. We call it ion implanters. Ion guns, they have a stream of atoms, boron or phosphorus, what you like to incorporate, and they shoot them down as high energy ions, and they occupy silicon where it's open. Silicon dioxide will work as a hard mask to protect where it's not wanted or welcomed. Whereas heat, you use the heat just to drive the diffusion. And if you do this, you get basically either this profile, or in the case of ion implantation, more a peaky profile, basically somewhere. And these are basically the regions which I have converted from N-type to P-type by incorporating or shooting in impurity atoms to change the P region to N and create this diode structure or junction structure. So you just made the simplest of all semiconductor devices, but guess it is one of the probably the most important device in human history. All solar cell technology, LED technology, transistors are simply multiple junctions conveniently placed for operation. All right, doping is done, etching. We want to etch, we want to remove. Although we have added material early on, doping is not deposition because we inserted impurity atoms to existing crystal. We didn't add a new layer. We added material into the crystal. Here we are removing material selectively, okay? Hopefully selectively, because that's what our intention is. And also we want to typically remove it from the top, but sometimes we want to go deep as well, okay? And there are some important things we want to, for instance, as we do this removal, we want to do this either equally happening in all directions, so it's a circular front or a spherical front of development. That's basically isotropic, or you want unidirectional removal, which is we call anisotropic. So sometimes you want straight down etching, sometimes you want to etch everything in that window, around that window in equal rates. And this is depending on which processes you use, and we have two options, wet etching or dry etching. Wet etching, as you would guess, use of solutions, wet solutions of acids and bases, typically. And it's a chemical process purely of reactions of materials that you select must remove what you are intending to remove. So if you're removing silicon, you need to have chemistry, typically nitric acid containing materials that react with silicon. And if you're removing silicon dioxide, it will be hydrofluoric acid, for instance, that readily attacks glass. Or if it's metal, it could be something else depending on the metal at hand. In the dry etch, we are using plasma, glowing plasma that you see, for instance, in this tube. There are so many atoms that are radicals. They are not stable and highly energized atoms. They want to react because they lost their electrons, or they need an electron. So they react with silicon and remove it. So on the left, you are on the top right, you're on the left side is an isotropic etch of circular profiles as materials are getting etched. And I believe very top layer is probably the mask there. Okay, you can see the mask has remained vertical most part. This is the mask for the most part. And underneath you see the circular etch here. And then there's even another etch, but that is more probably resistant etching sideways. Whereas this is more vertical etch, this is quite an anisotropic etch. Okay, so each one has uses. This is a very nice bit of semiconductor engineering where we learn how to make vertical profiles of walls and it plays a quite an important role in later on in the processes. The wet etching has two, you can do isotropic wet etching or anisotropic wet etching. So anisotropy is not just dry etch, or isotropic etch, only wet etch. Both can do isotropic and anisotropic etch depending on the chemistry. This is the wet version. In the case of wet, isotropic etching, something like HNA, which is a solution, or in the case of anisotropic, sodium potassium hydroxide etch or TMAH etch, they etch really the crystal planes precisely, because one crystal plane, what we call 111, which is diagonal direction in the crystal, doesn't etch at all because atomic density is so high, it doesn't provide enough etch rate there. So you can actually cleave off or expose atomic planes with extreme accuracy, as you could see here. So this is an anisotropic etch of potassium hydroxide of silicon. This wall angle is precisely 54 degrees, as you could see here. Yes?
I wanted to ask, how can it be so precise, like the etching is so aggressive, like wet etching is super aggressive, how can it be so precise and not cut off everything?
Very good question. That's one of the, I think chemistry and surface science is precise understanding of what happens is basically it does etch a little bit, because after all it etched from this way to that way. The etch rate is very substantially different. This is the 111 direction, 111 direction we call it. Etch is 400 times slower than this direction, or 300, 200 times, depending on the solvents you use. So what happens, the atomic density much lower, and in one plane, atomic density is higher on the other plane, so it just progresses. And there's a sweet spot, of course. If you use too high temperature, or if you use too high density of the solvent, as an acid or the base, it can go, those boundaries blur. But there's precisely surface engineering. In the case of this type of directionality, we use brute force, accelerated ions typically, in dry etching, we will come there. So there are various ways of doing wet or dry etching to precisely obtain this wall shape, which is one of the key things for success of many devices and technologies in semiconductors. Another thing is what type of crystal. So this is called 100 wafer. It means the cube of the faces of the cube point upwards. This is 110 wafer. It means cubes are rotated 90 and 45 degrees. So the cube is not like the peaking at the top as if. So the surface atom density and pattern is slightly different between 100 wafer and 110 wafer. That's why etch walls have different angles. So it's simply playing trick with the geometry of the crystal. Crystal is a perfect ordered atomic system. That's what we are gaining on. Etching, again, on the dry etching side, we use plasma. What was plasma? You fill a flask, a chamber with pure gas, you evacuate air, you put that gas, and you discharge a lot of energy, either forcing current through it, extremely large electric fields you establish, and the gas breaks down just like the lightning in our atmosphere. Just flashes start going on the electrical current and force through it, atoms disassociate, molecules disassociate, the radicals, and that environment is very volatile, very extremely volatile, and then we are using specialized chemistry for specialized etches. For instance, if you want to etch silicon, you want to use fluorine. If you want to etch other semiconductors and also metals, typically use chlorine. As you know, both chlorine and fluorine is very dangerous substances on their own. Because why? They have one electron, right? They want to give away, quickly react. And then that essentially is the gain, I'm sorry. They make it extremely volatile, but it's only when you're discharging the gas, okay? And you bring that plasma in contact with the silicon or the material. It doesn't have to be silicon. It could be silicon dioxide, silicon nitride, polysilicon. It could be the metal, you name it. And you have a mask protecting environment that you don't want to etch. And that volatile species, highly energetic ions, have an additional ability. So the physical sputtering is called these ions, and typically we use basically ions of the material that we will have some chemical compatibility. But those ions are also accelerating, beating down like little micro sort of bullets, okay? And they chipping away the material vertically. That's physical sputtering or physical etch. The chemical etch is the fact that we contain fluorine, which attacks silicon, okay? Also makes it etch. Normally you would etch, and if they were in contact, but that's 1 degree of etching. Plasma is the other, sputtering is other degree of etching, but the magic happens when you combine them two. Meaning, physical etching of accelerated ions will etch, but to some degree. Chemical etch will etch to some degree with some imperfections. When you combine them, you get all the benefits, and this graph shows that. On the left of this graph, you are seeing xenon fluoride exposed to silicon. There's a degree of etch very slow. And this is argon ions accelerating and hitting silicon surface. There's a degree of etch which is very small, 1 nanometer or less per minute. But when you combine argon ions and xenon fluoride gas together in a glowing discharge, the etch rate jumps up about 10 times. Okay? So there's a sweet spot in this plasma processes that allow you to that. But how do you strike the plasma? So there's a chemical process, there's a physical process, combination is all the better, but how do you get the plasma? Plasma is created either by pancake systems where 2 electrodes and you are discharging a radiation of RF frequency, typically 14.53 megahertz, I believe, or 15.63 megahertz. And that frequency is where a lot of the bombs in the gas vibrate. Okay, so that it absorbs that energy and starts glowing. You could do that, and it will look like this, and we will do a plasma process in the afternoon, hopefully. Okay, and it's just, why is it purple? Any guess? Anyone? Gas. In this case, oxygen. Okay, well, oxygen cleans the photoresist, the sticky, basically the resin material photoresist. It eats it up so easily, you get a squeaky clean wafer surface again. Oxygen attack. Oxygen radicals are just like fluorine and chlorine. They are in the same group, right? So they are really effective in removing organics. And this is some of the etch profiles of dry etching. Look how deep and smooth the etch vertically down. And then you could make lines, you could make circles, doesn't matter. But it does matter when you have extremely small patterns, the etch rate comes slower. Because the partial pressure and the atoms don't come vertically perfect. It's glancing angles, they start slowing down, having glancing collisions. But there's some more detail I skip. For instance, when you etch vertical like that, you etch a bit, you stop and you deposit a little bit to protect the sidewalls. Etch again, protect, etch again, protect, by just changing the oxygen ratio inside that gas. If you put enough oxygen, it binds with the etching gas and deposits as a protective film. And if you reduce it, then it starts etching again. So that there's some interesting tricks, and you could actually go through the entire, a third of the wafer sometimes in this process if needed, but it's long, of course, time consuming.
Wouldn't you be concerned with the oxidation of the various different metals in that process?
Very good. That's why we cover photoresist and or whatever material we want to cover with. We have to have a mask.
Okay.
Lithography.
Well, I thought you said you used oxygen in that bottom one to clean it.
Yes, but oxygen, whatever metal it is, well, that's added layer probably later, and then whatever it is has to be something that resists that. I agree. You can oxidize if you don't. But we are doing only 1 minute. We are not doing excessive energy or excessive. It's just organics burn very easily in oxygen. Next, deposition. How am I doing with time? I quickly lose of it.
Maybe a few minutes more.
Okay. Very quickly, deposition. We want to deposit. We want to add layers. And how do we do this? 2 methods again. Chemical vapor deposition, physical vapor deposition. Either you chemically cook up, just like you do in the kitchen, get the ingredients, heat up the pan, add them at right time, just simmer it right enough amount, right? And then the deposits form, and the byproducts float away in the vacuum system that's extracted. That's chemical cooking, that's chemical vapor deposition. Here we need to do extremely clean, pure materials with very precise temperatures. In the physical one, we use the brute force of material transfer from one source, whatever source it is, to the wafer by using mechanical tricks of heat or beating up with plasma ions. So PVD and CVD is the two general family, and then these are the parameters that you need to look at: the temperature, on rate, of surface coverage. Am I getting surface covered everywhere like the yellow material, or am I only I'm only coming down vertically, and only the top facing layers receive the material? And there are many deposition methods. We can possibly give an entire workshop on deposition methods, but these two classes are joined with some novel deposition techniques. I want to mention the atomic layer deposition in a minute, but you are seeing some of the deposited layers. For instance, that's a thermal CVD at some temperature. It's done, pulse PECVD means plasma in and CVD. Instead of temperature, we use the plasma to heat up the gas or energize the gas. And you are seeing at different temperatures, different layers are added. These are electron microscope images, that's why magnification is high. The physical vapor deposition, you use the brute force. Either heating, just like an incandescent bulb. In fact, incandescent bulbs would go bad, dark, because they would deposit their filament by heating and sputtering, kind of boiling off. Similarly, we boil off the metal from a point crucible onto the wafer in a vacuum chamber. It has to be evacuated, heated, and the material simply boils and goes in a line of sight because there's no air molecules to collide with. Or we use the plasma. In the case of plasma, we use heavy ions of argon. That plasma ions beat up to the target. So you literally chip away nanofeatures of nanofilaments of particulate matter of that target, and it flakes down just like snow onto the substrate, and the temperature is added a little bit for stiction, but temperature is much lower in this process compared to vacuum, the heating. And the heating can be done by purely passing current. You see the gold, I think gold for deposition, and this is the filament that is going to overheat by passing current. Or you see electron beam hitting a spot in that crucible. We create a focused electron beam under the crucible, gets hot without current flowing across. And then these things are always in vacuum chambers. Look at that vacuum chamber. There's a lot of pumps around it. There's some additional tools. This is not a production tool. I could see this a little more research. There's analytical instruments. Why? We want to see how good we are doing. Are we adding enough layers? Is it smooth enough? Is the chemistry correct? What if I'm ending up with raw material, right? Am I stopping at the right level? All this needs to be answered while you're doing the deposition. Okay. So CVD, okay, the CVD, on the other hand, is a controlled cooking, as I said, and it is either done at low pressure or slightly higher pressure, but depending on how we energize. You can use heat to energize the gases that we are cooking up in this pot, so to speak, or are we bringing them in precise pulsed amounts? That's called atomic layer deposition. It's a modern process, so novel, basically. What we can do is with atomic layer deposition, because we are not bringing copious amount of gas and cooking in wild amounts, we are not aiming at thick layers of 100 nanometer of insulator or 10 micron of insulator. If you need that kind of thick layer of insulator, you will need high temperature CVD. But in atomic layer deposition, you want 1-2 nanometer oxides to be formed. Just a precise amount, 5 nanometer. So you do them in precise pulsed. So in conventional CVD, you just bring the gases, elevate the temperature on the wafer, let the reaction happen, and the byproducts float away. In the atomic layer deposition, you pulse just enough material onto the wafer, it reacts with the wafer, then you clean it off with a purge gas, and then you bring the next gas, you puff it into the chamber, just right amount, and that reacts with the previous step, and then you clean it away step by step. Very much like basically an artist doing very, very fine detailed work on touching up the right time, right places. And then you end up basically that atomic layer thickness control. These are the three techniques that you talk about. We talked about. atomic layer deposition is essentially across, you could say, physical and chemical cooking, chemical, physical, and you can see a comparison. So if you want nice coverage everywhere, you typically do CVD. If you want vertical sidewalls not covered, you do the evaporation, typically, of metals, for instance. Okay? So these are very important. This is how we add materials, PVD and CVD techniques. Next is the chemical chemical mechanical polishing I mentioned earlier. As you make the materials, you make 20 layers of metallization. Okay, 20 layers of present. In 2 minutes, I will wrap up. All these metals build up sky, city line profile of high buildings, low buildings, gaps, narrow openings. How do you planarize so that you could do lithography with success in the next round? Especially as you build up the wafer. You need to fill the material with a sacrificial layer and polish, really fine polish, and painstakingly polishing process, wafer by wafer, and then eventually you get a very smooth surface which you expose and get rid of that sacrificial layer that you use for filling, and the material becomes shiny again. Last thing you want to do always is metrology. Well, you do metrology all across these 100 steps. You cannot take 100 steps and in blind faith here. At every step, you need to tell me if I succeeded or not. So we have to bring the instruments to do observations, either microscopic, electrical characterization, optical inspection, of course. We need to check if the materials that we created have enough stiction, they stick well, they don't peel away, they have the right thermal performance. So you have to do all sort of tests, all this thickness and line width measurements. You need to know exactly everything got the right way, both mechanically and electrically, and this is a cross-section of all these devices that have been created. So these are electron microscope images, and on the right-hand side, a new microscope called atomic force microscope used. As you can see, life isn't very smooth like we expect in the drawings. These are the interfaces of atomic layer deposition systems. Look, this is 10 nanometer. You're actually seeing crystal atoms locations using transmission electron microscopy. So this thing is about 3 nanometer, probably about 2 nanometer. Iridium, and there's a glues, there's silicon dioxide. So we need to inspect all these interfaces so we don't create traps, so that we can end up with chips, and these chips all lead to the transistors. Here's the level of complexity at the end of the day. This is electron microscopy image, beautiful image. And I think for the purpose of this image, they removed the oxide insulators in between. So you remember metal insulator, there's an acid that can etch all these insulators, leaving the metal work exposed by itself. I don't think there's any more complex human engineering than at any level. Remember, there's 20 billion of these transistors and modern chips, more than maybe, it's changing every day, and every one of them works. We cannot say 10% it's okay if you lose the 10%, we cannot say that. All right, folks, that's all from me.